Hi viewers, welcome to LMS Solution. Today we are going to see about grid connected PV system with the SEPIC converter and incremental conductance MPPT. This is Simulink model we created for a grid connected PV system. The system can generate around 100 kilowatts. So this is a PV panel. PV panel having 10 series connected model and 47 parallel strings. Single panel power is 213.15 watts. The open circuit voltage is 36.3 volt. The voltage at maximum power point is 29 volt. And short circuit current of the panel is 7.84 amps. And current at maximum power point is 7.35 amps. We are operating a PV panel with the different irradiation. Here you can see the PV and IV characteristics of the considered PV array. For 1000 watts per meter square, the maximum power is 100.2 kilowatts at operated at 290 volt. For 500 watts per meter square, the power is 50.75 kilowatts and operated at 293.3 volt. For 100 watts per meter square, the power from that PV array is 9.72 kilowatts and operated at 280.2 volt. This is a PV and IV characteristics of the considered PV array with the change in irradiation condition. And this PV array going to connect to the inverter via this converter. Here we are using SEPIC converter. The SEPIC converter going to be designed based upon the power rating of the PV array. Here power rating we are having around 100.2 kilowatts, and then input voltage of the converter is around 290 volt, and output voltage of the converter we are going to consider as 600 volt. Based upon this parameter, we have to design this L1, L2 and then C1 on C2. And here we have the incremental conductance MPPT. So here we are going to measure the PV voltage and current that going to be processed via incremental conductance MPPT. Inside the incremental conductance MPPT, here the condition, here we need to measure the PV power, change in voltage, change in power, change in current, and then here we are going to calculate another parameter, nothing but M nothing but absolute value of change in power divided by change in voltage. So initially here we need to check the value of M, whether M is less than 0.05, then that means it going to be considered as the PV array already operated at maximum power point condition. We have to maintain the duty cycle is a previous duty cycle. No need to change anything during this condition. If suppose the M value is not less than 0.05, then we have to check the condition of change in voltage. If change in voltage is equal to 0, then we need to check the condition, the change in current. Both the change in voltage and change in current equal to 0, then already PVL is operated at the maximum power point condition. So no need to change the duty cycle. Just you have to maintain the duty cycle as a previous duty cycle. If suppose the change in current is not equal to 0, then you have to check the change in current whether it's greater than 0 or not. If it is greater than 0, so we need to decrement the duty cycle by using this formula, D equal to D volt minus M into delta T, or else we need to increment the duty cycle by using this formula, adjust the voltage of the PV array in order to get the maximum power from the PV panel. If suppose this change in voltage is not equal to 0, then we need to check this condition. So here we need to check the condition of incremental conductance. dI by dV is equal to minus I by V. If it is dI by dV equal to minus I by V, then the PV panel is operated at maximum power point condition. Then no need to change the duty cycle. You have to maintain the duty cycle which is equal to previous duty cycle. If suppose the dI by dV is greater than minus I by V, then we need to decrement the duty cycle by using this formula, or else you have to increment the duty cycle by using this formula in order to adjust the PV array voltage in order to get the maximum power from the PV panel. After modification of duty cycle, we need to check the duty cycle with the maximum or minimum limit. If suppose it exceeds the maximum or minimum limit, then we need to make the duty cycle that should be follow the previous duty cycle, and then the override the detail here. The current instant duty cycle voltage power current will be overrated with the previous instant duty cycle voltage power and current. So this will be keep on executing in order to get the maximum power from the PV array. And then finally here we are getting the duty cycle The duty cycle going to be the compare with the sawtooth waveform in order to get the pulse for the SEPIC converter. This pulse will be control this IGBT in order to extract the maximum power from the PV panel. And then this output of SEPIC converter going to be connected to this inverter, voltage source inverter, and then the voltage source inverter going to be connected to the grid. Here we are having grid around 400 volt with a frequency of 50 Hz, and then you're going to be connected via this LCL filter. And then this voltage source inverter going to be controlled by means of feed-forward decoupling control concept. Further, we need to measure the DC-link voltage, otherwise called we need to measure the output voltage of the SEPIC converter, and then it going to be compared with the reference voltage. So already I told here we need to maintain at 600 volt. So that's why we are going to compare that DC link voltage with the 600, and it going to be processed via PA controller. This PA controller output will be considered as a ID reference. So this ID reference going to be compared with the ID. So ID and IQ nothing but the direct and quadrature axis current of the grid current. That means grid current, otherwise called as the inverter current. Here we need to measure the inverter current. That inverter current will be converted into DQ not form by using power transformation. And in order to apply the power transformation, we need omega t. For that, we have to use PLL concept in order to generate the omega t. Here we have conversion VABC to VD VQ, and here we have another conversion IABC to IDIQ. Here we are applying that the power transformation concept. This voltage controller will provide the ID reference. So the ID reference going to be processed compared with the actual ID of that inverter current, and it going to be processed by this PA controller. And here we are going to apply that feed forward decoupling concept for a D-axis control. And then here we are going to only sending the real power from PV to grid via this inverter and this SEPIC converter. Here we are making IQ reference equal to 0, and then again it going to be compared with IQ. That means IQ current of the inverter and process via PA controller. And then here we are applying that the feed forward decoupling control concept of the Q axis current. And finally we are getting here control voltage in the form of VD and VQ. They going to be converted into ABC by using inverse power transformation, and then it going to be compared with the triangular wave for generating the pulse. This pulse going to be used for control this inverter and how to get the power from the PV and then inject it to the grid. This is the working of this model. Now I am going to explain the simulation result of this model. First, here I am going to change the irradiation, and then I am going to see the result of the system. Here we create change in irradiation condition from time 0 to 0.4. We are going to maintain the irradiation equal to 1000 watts per meter square. After 0.4 second, the irradiation changed to 800. From time 0.5 to 0.8, the irradiation maintained at 800. After 0.8 second, the irradiation changed to 500. From 0.9 to 1.2, the irradiation maintained at 500. After at to 1.2, the irradiation changed to 300. From 1.3 to 1.6 second, the irradiation maintained at 300 watts per meter square. For this situation, you have to check the result of the system. So I am going to simulate this model, and then I am going to explain the result. Here, this is the result of PV power. For 1000 watts per meter square, here we are getting around 100 kilowatt power. And then this is the grid voltage and grid current, and this is the grid power. Here we are getting around 100 kilowatt power. That means whatever power we are generating from the PV is going to be sent to the grid. And also I am going to expand this one. Here you are seeing that the current and the voltage are sinusoidal. After 0.4 second, what happened? The irradiation changed from 1000 watts per meter square to 800. Because of that, the PV power changed to 80 kilowatts. And then you can see that small deviation, that means the power reduction during that change in irradiation also. Here also you can see that after 0.8 second, the irradiation changed from 800 to 500. Here you can see that we are getting around 50 kilowatts. At time of 1.2 seconds, the irradiation changed from 500 to 300. Because of that, we are getting around 300 kilowatts. So, and also here you can see that because of the reduction in the PV power, that current also, injecting current to the grid also going to be reduced. Like that, we can see that the current and the amplitude also reduced. It means water power we are generating from the PV power is sent to the grid. And also here you can see that this the grid power. Here also you can see here the power will be reducing because of reduction in the irradiation. This is a result of the grid connected PV system with the SEPIC converter and the incremental conductance MPPT algorithm. Thanks for watching our videos. Kindly subscribe our channel and also click bell icon for notification about upcoming videos. Thank you. Thank you so much. Bye bye.